Hey everyone, welcome to the Chapter 2 review video for the final exam. So Chapter 2 is all about differentiation, and let's remind ourselves what the derivative is. So the derivative of a function f of x is another function that takes an x value as an input, and it tells you the slope of the tangent line to f of x at that given x value. And the way we compute it is by solving this thing here, the limit as h goes to 0 of f of x plus h minus f of x over h. So let's look at two examples of solving something with the limit definition of derivative. So this first one here, use the limit definition of the derivative to compute the derivative of f of x equals the square root of x plus 1. So if this is f of x, then we need to know what f of x plus h is. F of x plus h here would be the square root of x plus h plus 1. Right? When we're trying to find f of x plus h, we just go anywhere we see an x and we replace it with x plus h in parentheses. So what we're trying to solve is the limit as h goes to 0 of the square root of x plus h plus 1 minus the square root of x plus 1 all over h. And when it comes to doing the limit definition of the derivative, ultimately our goal is to cancel this h out with something. Normally we're going to end up factoring an h out from the top, and then the h on top and bottom are going to cancel, because right now if we try plugging in, we'll get a divide by 0 error, which is no good. So what can we do to simplify this? Well, if we think back to covering the algebraic solutions of limits in section 1.5, if you watch the first review video, we can multiply by the conjugate. Multiplying by the conjugate is a really good idea if we have random square roots floating around and we want to simplify. So in order to multiply by the conjugate, we're going to multiply the top by square root of x plus h plus 1, plus, we're going to flip this symbol from a minus to a plus, the square root of x plus 1. And if we multiply by something on the top, in order to maintain equality, we have to multiply by the same thing on the bottom. And this will give us the limit as h goes to 0 of, and if we FOIL this out, we'll end up with x plus h plus 1 minus x plus 1. All over h times root x plus h plus 1 plus root x plus 1. And the reason we get this is it ultimately comes back to the difference of squares. So remember, the difference of squares is a squared minus b squared equals a plus b times a minus b. Here we have our a minus b. If we multiply it by a plus b, we get a squared minus b squared. So a squared is the square of the square root of x plus h plus 1. We get x plus h plus 1 minus b squared. And our b here is square root of x plus 1. So when we square that, we get x plus 1. So altogether, this simplifies to be the limit as h goes to 0 of x plus h plus 1 minus x minus 1 over h times root x plus h plus 1 plus root x plus 1. We get nice cancellation here on top. The x's and the 1's all cancel out. So we're left with the limit as h goes to 0 of h over h times square root of x plus h plus 1 plus the square root of x plus 1. And huzzah, we finally got the thing on top that cancels out with the h on the bottom. So now we have the limit as h goes to 0 of 1 over the square root of x plus h plus 1 plus the square root of x plus 1. And now we're in a position where we can just plug in h equals 0, and we're not going to break anything. And if we plug in h equals 0, we're going to get 1 over the square root of x plus 1 plus the square root of x plus 1, which is just 1 over 2 square root of x plus 1. So that's one example of using the limit definition of the derivative to actually define the derivative. The other example I want to look at is this one. Use the limit definition of the derivative to compute the derivative of f of x equals x cubed minus 4x. So again, in order to compute the limit definition, we need to know what f of x plus h is. And the way we find f of x plus h is we look back at our original function, and anywhere we see an x, we replace it with an x plus h in parentheses. So here we're going to get x plus h cubed minus 4 times x plus h. So let's write out our limit definition. We're looking for the limit as h goes to 0 of f of x plus h minus f of x. And here it's important to put the entirety of f of x in parentheses because we're subtracting off this entire quantity all over h. And now let's simplify the top. And by simplify, I mean let's expand everything, get cancellation, condense things as best we can. Expanding things on top. This term here is going to become x cubed plus 3x squared h plus 3xh squared plus h cubed. We can distribute this minus 4 here and here to get minus 4x minus 4h. And then we distribute this negative in here to get minus x cubed plus 4x. And this is all over h. Now, what nice cancellation do we get on the top? This x cubed and this minus x cubed are going to cancel. Minus 4x and plus 4x are going to cancel. So we get the limit as h goes to 0 of 3x squared h plus 3xh squared plus h cubed minus 4h all over h. And now we are in a really good spot because each term here in the top has an h in it, so we can factor an h out to give us the limit as h goes to 0 of h times 3x squared plus 3xh plus h squared minus 4 all over h. And huzzah, we get the cancellation. And so now we have the limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 4. And now we can just plug in h equals 0. And if we plug in h equals 0, well, this term doesn't have an h in it. This term will become 0 because we're going to multiply 3x by 0. This is 0 squared, we get 0. And lastly, we have a minus 4, which doesn't change. And so our derivative is 3x squared minus 4. Now, using the limit definition can be a real pain, and it can take a lot of time. But it's definitely useful to know, especially on the final, when I can almost guarantee there will be a question like this. But the good news is we don't have to do this all the time. We have a lot of rules of differentiation that can super streamline everything for everything for us. So here we're going to have c be a constant. The derivative of a constant is 0. If we have a constant times a function, then the derivative of that constant times a function is the same as the constant times the derivative of that function. We can factor a constant out of differentiation. Differentiation distributes over addition, so the derivative of f plus g is the derivative of f plus the derivative of g, which is nice. This means we can go term by term when differentiating. And then last but not least, the most important rule of all, probably the one that we all use most often, is this guy here. The derivative of c times x to the n is c times n times x to the n minus 1. We bring the exponent down and subtract 1 from the exponent. So let's put these in action. Let's compute f prime if f of x is 4 times 3x squared plus 7x plus 1 over x. Because we have this rule here that really helps us if we have something times x to an exponent, it really helps to rewrite everything as exponents. So we have f of x equals 4 times 3x squared plus 7x plus x to the minus 1. And now when we take the derivative, f prime of x is 4 times the derivative of 3x squared plus 7x plus x to the minus 1. And remember, we can bring out this 4 thanks to this rule here. And this gives us 4 times 6x plus 7 minus x to the minus 2. And to get this term, and this term, we just followed this rule here. Alternatively, and possibly more easily, we could also distribute this 4 in here to get f of x equals 12x squared plus 28x plus 4 times x to the minus 1, and then just apply this rule over and over and over again to get us 24x plus 28 plus, or I should say minus, 4 times x to the minus 2. So that's using the rules of differentiation. Other rules that are important include the product rule. And the product rule says if we have a function that's a left part times a right part, so a multiplication of two functions, a product of two functions, then the derivative is LDR plus RDL. So let's use this product rule to compute the derivative of f of x equals 6x squared plus 1 times 7x cubed plus 1 over x. And again, like before, it's always helpful to rewrite everything as exponents if we can. So let's rewrite that 1 over x as x to the minus 1. Then our left part is 6x squared plus 1. Our right part is 7x cubed plus x to the minus 1. The derivative of the left part would be 12x. And the derivative of the right part is 21x squared minus x to the minus 2. If we throw this all together, we get that the derivative is f prime of x equals L times dr plus the right-hand side, or r, which is 7x cubed plus x to the minus 1, times dl, which is 12x. And that's our derivative. The cousin of the product rule is the quotient rule. And so the quotient rule says if we have a function f of x, which is a top part divided by a bottom part, then f prime is bo dto minus to dbo over bobo. So it's the bottom part times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So let's take the derivative of this function. F of x is 6x squared plus 1 over 7x cubed plus 1 over x. And again, as always, it's helpful to write everything with exponents. So we're going to write the 1 over x as x to the minus 1. So now our bottom part is 7x cubed plus x to the minus 1. Our top part is 6x squared plus 1. Our dbo, the derivative of the bottom, is 21x minus x to the minus 2. And our dto is 12x. If we throw all these in the pot, throw all our ingredients together under this formula, we get that f prime of x is bo dto, so 7x cubed plus x to the minus 1 times the derivative of the top times 12x minus to dbo, so that's minus 6x squared plus 1 times the derivative of the bottom, 21x minus x to the minus 2, all over the bottom squared, all over bobo, which is 7x cubed plus x to the minus 1. We're going to square that whole thing. So that's our derivative there. That's the quotient rule. I am kind of going a little quickly through these derivative rules, but part of that is because y'all have done so many derivatives at this point in the semester. I assume you probably gag every time you see you have another derivative to take. But there is one more rule we need to go over, and that is called the chain rule. And for the purposes of this class, pretty much the only chain rule you have to remember is that if our function f of x is a number times g of x to the n power, where g of x is some function of x, then f prime, the way we compute f prime, is we kind of follow the same rule as before. We bring the exponent down and subtract 1 from the exponent, but then we have to multiply by the derivative of g of x. So let's see this in action. Let's say we're given this function here, f of x equals 4 times x squared plus x cubed. To take the derivative, we bring the exponent down, subtract 1 from the exponent, and then multiply by the derivative of the inside, which is 2x plus 1. Or let's say we have this function. F of t is the square root of 2t squared plus 5t plus 2. Again, always write everything as exponents if you can. So we're going to write this square root as a 1/2 power. And now it's really clear that our function f is just some function raised to a power. So when we take the derivative, we're going to have f prime of t equals 1/2 times 2t squared plus 5t plus 2 to the minus 1/2, because 1/2 minus 1 is minus 1/2. But then we have to multiply by the derivative of the inside here. And this will give us 4t plus 5. So that's the chain rule. So we covered our big rules, our product rule, our chain rule, and our quotient rule. Let's throw them all together. I've got two examples here which involve all of the rules kind of meshed together. So here on the left-hand side, let's focus here for at first. We have a quotient rule because we have, a fraction. But let's begin first by writing everything with exponents. Okay, so instead of that cube root, we're going to write to the 1/3 power. So then our bottom part is 2 minus 9x cubed. Our top part is 9 times 4x squared plus 3 to the 1/3. The derivative of the bottom is 3 times 2 minus 9x squared times minus 9. And the derivative of the top part is 3 times 4x squared plus 3 to the minus 2/3 times 8x. So we have our bottom, our top, our derivative of the bottom, and our derivative of the top. If we throw them all together, we get that f prime of x is bow dto minus toe dbow. I'm going to run out of room, aren't I? It's all fun and games till I run out of room. We'll squeeze in our minus 9 right there. Look at that. All over the bottom squared. So all over 2 minus 9x cubed squared. So there's that one. And then this red function over here, let me just copy and paste it. Copy, paste. Here we need to use the product rule because we have things multiplied together. But let's first begin by writing everything with exponents. So we have 4 minus x cubed cubed, and we're taking the 4th root of that. So this becomes 4 minus x cubed to the 3/4 power. When we have fractional exponents, the top exponent means like raise it to that power, and the bottom part, the denominator of the exponent, means take that root. So something raised to the 3/4 power means cube it and then take the 4th root. Or alternatively, take the 4th root and then cube that. So our left-hand part is 7x squared to the 5th. Our right-hand part is 4 minus x cubed to the 3/4. The derivative of the left is 5 times 7x squared to the 4th times 14x. And the derivative of the right is 3/4 times 4 minus x cubed to the minus 1/4 times minus 3x squared. Okay, just using chain rule. So if we throw those all together into our thing LDR plus RDL, we get L times dr, 3/4 times 4 minus x cubed to the minus 1/4 times minus 3x squared, plus R dl, 5 times 7x squared to the 4th times 14x. And that's our derivative of that. Okay, one thing to note here, If you ever see marginal profit or marginal cost or marginal revenue, you can read marginal as derivative of. So for this example here where it says find marginal revenue of r of x equals minus x squared plus 30, that means find the derivative of revenue, where revenue is that. So our goal is just to find r prime of x, which we can use our standard rules to figure out pretty easily that it's minus 2x plus 30. All right, but with that out of the way, let's talk about implicit differentiation. So implicit differentiation happens if we have an equation, notably not a function, an equation, and we need to find dy dx. And in order to do that, we're going to take the derivative of both sides with respect to x. And if we come across a term with a y in it, we take the derivative as usual, but we have to multiply by a dy dx. Okay? So I have two examples here. Let's take a look at both of them in action. The first one says find dy dx at 2, negative 1 of this given equation. Okay? Let's go term by term. We're going to take the derivative with respect to x of both sides. Going term by term. For x squared y, this we have to use the product rule because y is a function of x. Like the value of y implicitly depends on x. If you give me a value of x, my value of y is kind of determined. So our left-hand thing is x squared. Our right-hand thing is y. So then dl is 2x. To find dr, we take the derivative as normal. So the derivative of y, if we apply our standard rules, we get 1. But then we have to multiply by a dy dx. So throwing that all together, we get LDR plus R dl, so plus 2xy, plus, and then for this term, y cubed x. I'll come over here. Why does it keep scooting up? Y cubed x. Our left-hand thing is y cubed. Our right-hand thing is x. To find dl, we're taking the derivative of something with y in it. So we apply our standard rules. We get 3y squared. But then we have to multiply by a dy dx. Okay? And this is just because we're using the chain rule, right? So chain rule says derivative of the outside times derivative of the inside. Y here is our function of x. So to find the derivative, we apply our standard rules. We get 3y squared. And then we multiply by the derivative of the inside function. And our dr is just 1, so we throw that all together. We get LDR is just y cubed plus r times dl is 3y squared dy dx. And then the right-hand side of the equation just gives us a 0 when we take the derivative. So now I'm kind of running out of room, but I'm going to do my best. We're going to get everything that has dy dx in it to one side and everything else to the other. So we end up with x squared dy dx plus 3xy dy dx equals minus 2xy minus y cubed. And then we can factor out a dy dx and divide. So then we get dy dx equals minus 2xy minus y cubed over x squared plus 3xy. And now that we have this, we can plug in x equals 2 and y equals negative 1 to get minus 2 times minus 1 minus minus 1 cubed over 2 squared plus 3 times 2 times minus 1. And this works out to be about, I'd reckon, 4 plus 1 over 4 minus 6, which is 5 over minus 2. And that's our answer for that. Okay? But let's take a look at another implicit differentiation problem, just to really get in our heads. X cubed plus y cubed equals 6xy. It might be helpful here to get everything that has an x and y in it to one side and get all of our constants to another. So this equation here is the same as the equation x cubed plus y cubed minus 6xy equals 0. And let's take the derivative of both sides with respect to x. Going term by term, the first term, we get just 3x squared. We apply our standard rules. The next term, the derivative of y cubed with respect to x, we're going to get 3y squared times dy dx minus, and let's talk about the derivative of 6xy. So the left-hand thing is 6x, the right-hand thing is y, the derivative of the left-hand thing is 6, the derivative of the right-hand thing is a dy dx. So if we throw that all together, we're going to get LDR plus RDL. Notice here I am subtracting off the entire derivative here, so I put that derivative in parentheses. So we have this minus 6 here. The minus gets carried down over here, but we're taking the derivative of this and putting that entire derivative in parentheses. All right, so let's simplify this a bit. We get 3x squared plus 3y squared dy dx minus 6x dy dx minus 6y equals 0. So then, as we did before, we're going to get every term that has a dy dx in it onto one side and every other term onto the other side. We're going to factor out a dy dx. And then we're going to divide to get finally that dy dx equals minus 3x squared plus 6y over 3y squared minus 6x. And that's our final answer. Now, a natural question is, what is implicit differentiation good for? Can we use it in anything? And the answer is yes. And that brings us to related rates. And the idea of related rates is if x and y are two functions of time that are related by some equation, then dx dt and dy dt are related too. Okay? And let's see how this works in action. Just as a refresher, the example says a 13-foot ladder is leaning against a wall when suddenly the bottom of the ladder slips away from the wall, begins to slide down the wall. The bottom is moving away from the wall at a rate of 1 foot per second. How quickly is the top of the ladder falling when the bottom of the ladder is 5 feet away from the wall? So let's draw a picture here. Let's say we have a wall here, and then resting against that wall we have our ladder. Our ladder is 13 feet, and this distance here we can call x, and then this distance here, the vertical distance, I didn't draw that very well, the vertical distance here we can call y. So what all do we know? We know that the bottom, sorry, didn't mean to show you all my grocery list. Here we are. Sorry about that. That was random. I'll probably edit that out. What do we know? So our ladder is 13 feet. It's leaning against a wall. And the bottom of the ladder begins to slip away from the wall at a rate of 1 foot per second. So that tells us that the change in x with respect to time, or dx dt, equals 1. We also know that the bottom of the ladder is 5 feet away from the wall, so x equals 5. And our goal is to figure out how quickly is the top of the ladder falling. So our goal is to find dy dt. So is there an equation that can relate x and y together? And there is. It's the Pythagorean theorem. We know that x squared plus y squared equals 13 squared. That's our equation. And in order to find dy dt, let's take a derivative of both sides with respect to t. going term by term, the derivative of x squared with respect to time, not with respect to x, we use implicit differentiation to find the derivative is 2x times dx dt. Plus, and then here the derivative of y squared with respect to time, we get 2y dy dt equals 0. 13 squared is 169. We take the derivative, we get 0. So now we get everything with dy dt to one side. We get that 2y dy dt equals minus 2x dx dt. And so then finally we have that dy dt equals minus 2x times dx dt all over 2y. We know our value of x, we know our value of dx dt. The only thing we're missing is the value of y, but we can find that because we know that 5 squared plus y squared equals 13 squared. Right? We're plugging our given x value into here to tell us our y value. So 25 plus y squared equals 169. Y squared equals 144. Y is 12. So if we plug all of our stuff that we know into dy dt, x equals 5, dx dt equals 1, we're going to get minus 5 over 12. Dy dt equals minus 5 over 12. Related rates. And while I'm here, I'm also going to go a little bit into Chapter 3, because we covered a lot of Chapter 3 in the previous review videos. But there's 2 sections we need to cover. Increasing and decreasing functions and maximums and minimums. So a function is increasing on an interval ab if f prime of x is greater than 0 on that interval. And similarly, the function is decreasing on ab if f prime of x is less than 0. So if f is increasing, respectively decreasing, on 2 adjacent intervals a, b, and b, c, then f is increasing, respectively decreasing, on a to c. So for example, let's find the intervals on which f is increasing or decreasing. Step 1 is we need to take the derivative, set it equal to 0. So f prime of x is going to be 3x squared minus 12x. We can factor out a 3x from both of these to get x minus 4. And this tells us that x equals 0 or x equals 4. And so now we can use this to break the line into chunks. So we have the chunk from minus infinity to 0, the chunk from 0 to 4, and the chunk from 4 to infinity. And now we pick a number from each of these. I'll pick minus 1, 1, and 5. Actually, I'll pick 10. And now we test the first derivative with these. So we test f prime of minus 1, f prime of 1, and f prime of 10. If we plug minus 1 in here, we're going to get 3 plus 12 equals 15, which is bigger than 0. If we plug 1 into the derivative, we're going to get 3 minus 12 equals minus 9 is less than 0. And if we plug 10 into the derivative here, we're going to get 300 minus 120, which is definitely bigger than 0. So f is increasing on minus infinity to 0 and 4 to infinity, and decreasing on 0 to 4. All right, and one more of these that I'm going to just rush through. The same idea of finding where we're increasing and decreasing, we can also use it to find maximums and minimums, right? Because if we know we're increasing to the left of a point and decreasing to the right of it, we know that we're at a maximum. If we're decreasing to the left, increasing to the right, then we're going to be at a minimum. So here we have this given function. We can take the derivative and set it equal to 0. And here we can factor out a 6x from both of these. We're going to have 2x minus 3. So this gives us that x equals 0, or x equals 3 over 2. All right, so now we have our intervals, minus infinity to 0, 0 to 3 over 2, and 3 over 2 to infinity. Let's pick a point from each of these. I'll pick minus 1, 1, and 10 again. That's really handy. F prime of minus 1 is going to be 12 plus 18, which is definitely bigger than 0. F prime of 1, if we plug 1 into here, we're going to have 12 minus 18 is negative 6, is less than 0. And if we plug in 10 into our derivative, we're going to have 120, or we're going to have 1200 minus 180, which is definitely bigger than 0. So f is increasing on minus infinity to 0 and 3/2 to infinity. And it's decreasing on 0 to 3/2. So we have a minimum at x equals 3/2 and a maximum at x equals 0. Now all that's left to do is to find the appropriate y values, and then we're done. But I'll leave that to you because that's just plugging something into a calculator. Thank you so much.